Indeed, it's the last day of SILAFAE, so welcome everybody to this last day of this very intense week. And in this session, we will have 3 talks from 3 of the LAC experiments, starting with Alice. So welcome, Cristiane Jahnke, and she's going to tell us about the perspective, prospects, and of the Alice experiment.
Okay, thank you very much. It's a pleasure to be here to present some highlights and perspectives from the Alice experiment. You can see my slides moving, right? Okay. So the first thing that I would like to say is what we studied with Alice. We studied several different collision systems. We have studied the heavy ion collisions like lead-lead and Shannon-Shannon collisions. And in this kind of collision, what we expect is the formation of the quark-gluon plasma. And then we wanted to study its properties like equation of state, transport coefficients, and we can also study the in-medium energy loss, since it's expected that there is a color charge and quark mass dependence. And we can also study thermalization of heavy quarks and quarkonium dissociation and regeneration. And we also studied with Alice p-lead collisions. And in this kind of collisions, what we expect is to study closed nuclear matter effects. And then we can study the nuclear modification of the parton densities and also the propagation of particles in the nucleus or in a medium that can be created in just collisions. And we also have PP collisions, and they can serve as reference to studies of lead-lead and p-lead collisions. And they can also be used to study several aspects of the QCG. And with the latest results from Alice, we also have seen that in PP and p-lead collisions, we can have some collective behavior, even that they are small systems. So we also show a little bit of that on this presentation. But first I want to say why we study heavy quarks. And heavy quarks, as you probably know, are particles that contain charm and build quarks. And with Alice, we can measure the J-psi, psi2s, upsilon states, and we can also measure what we call open heavy flavor, like the meson, the meson, and this lambda, sigma, and key when they have a charm or a build quark. And why it's interesting to measure them is because they are produced in the very early stages of the collision here, and they can traverse all the QGP formed in heavy ion collisions, since they live much longer than the duration of the QGP. So we can have information about the QGP using heavy flavor particles. And also, the quarkonium state was proposed several years ago as a signature of the QGP, since they can melt on the QGP, as I show on this plot here. And we have this sequential melting proposal, but with the latest results from the LHC, we see that actually there is another competing process, which is called the regeneration. So with the Alice data, we can test and check these properties. And why we study light quarks? Light quarks are all just particles that we list here that has up, down, and strange quarks. And we can measure several of them with Alice. And they are interesting since they can be produced on the hard scattering, but also inside the QGP. So they can bring us information about the QGP, in particular about the hydrodynamic expansion and also the mechanism of hadronization. So we measure these particles and we can compare with model calculations like the statistical hadronization model or coalescence model, and we can learn about the hadronization of particles. And also, when we measure strangeness, we can use then as a signature of the QGP, since the strangeness enhancement was proposed as a signature of the QGP. And we also can use light quarks and strange quarks to study the interaction between hadrons and also what we call nucleosynthesis in hadronic collisions. And how we do that with ALICE? In the case of heavy quarks, we can reconstruct them via hadronic decays. For example, we can reconstruct the prompt and non-prompt G-meson based on the vertex decay topology. What we call here non-prompt G-meson are actually the D-meson that comes from B-meson. So it's charm coming from beauty. And the prompt one is only charm. So we can separate the sources. We can also reconstruct like the charmed lambda using their hadronic decays. And you can also use the semi-leptonic decays of B and G meso to reconstruct them. And you can separate electrons from beauty from electrons from charm, also based on the fact that the beauty quarks has a longer lifetime. So we use the GCA distributions, and you can separate beauty and charm particles. And we can also measure quarkonium in the dielectron or dimuon pairs based on the invariant mass distributions. And in the case of light quarks, we can measure several of them directly from the signal in our time projection chamber. And we can also reconstruct several of them, as I have listed here a few examples. And about the observables that we usually use, I have listed here the main ones, which are spectra, particle yields, jets, correlations. And one important observable that we have been using is the nuclear modification factor, which is given by this expression. Here is the yield that we can measure for a given particle in heavy ion collisions divided by what we have in proton-proton collisions normalized by TAA. And this TAA is a normalization in order to have the same number of binary collisions in heavy ion collisions and proton-proton collisions. So if the RAA is around 1, we can say that there is no hot medium effects or no cold nuclear matter effects. However, if it's smaller than 1, we can have effects from the QGP or from the cold nuclear matter effects. And to separate hot and cold nuclear matter effects, what we do is to measure it in lead-lead collisions, and then we measured again in P-lead collisions, where we expect to quantify the cold nuclear matter effects. And in the case of heavy quarks, the energy loss is expected to be mass dependent, as I show on this expression. So we expect that light particles will lose more energy than charm and beauty, and this will be reflected on the nuclear modification factor like that. And another important observable is the anisotropic flow. So when we have a collision which is not central, we will have this spatial anisotropy of the created particles, and this will be converted in momentum anisotropy due to the different pressures that you have. And then if you measure the V2 from this expression, we call it elliptic flow, and it indicates the collective motion and thermalization of particles, and V3 will indicate event by event fluctuation. So we have also measured this with ALICE. And how we do all of that? We use the ALICE detector. This is an schematic view of the ALICE. It's composed by two main parts, one at mid rapidity, which is formed by several slices of detectors. So that's the beam pipe, and here is the interaction point, and this green detector is the inner tracking system that is responsible for vertex and also tracking. Then we have this blue detector with our time projection chamber that is used for tracking and also for particle identification. Then we have the transition radiation detector, the time of flight, and the electromagnetic calorimeter that are used for particle identification. And this is at mid rapidity, and at forward rapidity, we have our muon tracking, which is also a trigger. And on this table, I have listed the systems that we have measured so far, the years that the data were taken, and also the energy and the integrated luminosity that we could achieve in each of these systems. Okay, so now I'd like to show some of our results in lead-lead and Shannon-Shannon collisions. Starting with the open heavy-flavour RAA, which is the nuclear modification factor that I showed a few slides before. So these are the RAA as a function of transverse momentum. The first plot, we show the comparison of results for pion in red with G meson in black. And we also have results here in green for J psi. And what we can see from this plot is that the nuclear modification factor of pions is smaller than the one from G meson. On the middle plot, we show the nuclear modification factor as a function of transverse momentum for prompt and non-prompt G meson. So again, the non-prompt is the ones that come from B meson. So in this case, we have a comparison of RAA from C going to G meson and B going to G meson. And we see that the RAA of C is smaller than the RAA of B. Following the mass ordering that we expected. And on this third plot, we show the results also of the nuclear modification factor as a function of momentum for electrons from C and B combined, which is just black points, compared to the electrons coming only from beauty, where we could separate the contributions from C and B. And you see that there is a hint that the energy loss of electrons from C and B is higher than the one from only electrons from beauty. So this is reflected on the RAA like that. So we have this RAA ordering. This can be related to the different energy laws of these different species of particles on the QGP, but can also be related to the different radial flow of these particles. Okay, so to learn what's happening, what we usually do is to compare with models. So on this slide, we show several model calculations that try to explain the prompt de meson, and on the second plot is the non-prompt de meson, and the third plot, the prompt over non-prompt de meson. And what we see from the several model calculation is that some of them includes only the collisional energy loss, while others includes collisional plus radiative energy loss, and they all can describe our data at least qualitatively. And some of them also includes quark recombination. Okay, we also have the nuclear modification factor of J psi. So here I show the nuclear modification factor as a function of centrality. And on this first plot, what's interesting to see is that we have two results from ALICE, the lead-lead collisions at 5 and lead-lead collisions at 2 TeV, which are the red and green points. And it's compared to the results from RIC, which are the blue points. And what we can see is that there is a weaker suppression at a higher collision energy. And this effect is predicted by the regeneration models. And on this plot on the middle, we show the inclusive J psi at mid rapidity, and the inclusive J psi at forward rapidity is shown on this last, on this third plot. And we compare to several model calculations, and all of them can describe, at least qualitatively, our results. On the next slide, I show the pitch dependency of these results and a comparison of the mid and forward rapidity. And what we have seen is that at forward rapidity, we see a stronger suppression at low momentum, while at high momentum, we see a similar suppression. And we have two models calculations that try to explain this, and they explain, at least qualitatively, this difference between mid and forward rapidity. We have also measured the elliptic flow Here I show the results for light flavor. In lead-lead collisions, the elliptic flow, as I said before, we call it V2, and they were measured as a function of momentum. And this was done for several species of light flavor particles. And for low momentum, we see that there is a clear mass ordering, as you can see in all of these plots. And this is expected from the hydrodynamics. We also have measured it for heavy flavor. So here we show the comparison of the pions result. It's very precise because we can measure a lot of pions. And we have the results from prompt G meson, inclusive J psi, and also electrons from beauty and upsilon. And what we have seen is that there is a positive V2 for prompt G meson, J psi, and B going to electrons. In the case of upsilon, the results are compatible with 0. And there is a mass ordering that can be observed. However, this is only for low PT, but for intermediate PT, we started to see that the V2 of G meson is close to the V2 of pions, and this can be due to the charm quark thermalization. And also for very high PT, there is a hint that the V2 of J psi is also close to the one of G meson and pions, and this could be explained as a similar path length dependence of energy loss. But I put here a question mark because this is just a possible explanation. Okay, then we also have measured the triangular flow, and this was done for pions with a very high precision, and then for G meson and J psi in red. And what we can see is that there is a V2 for prompt G meson, J psi, and pions, and they are different from 0. So it's an indication that charm quarks are sensitive to initial state fluctuations. And also we have measured several quantities in different collision systems. So here I choose just one result to show the comparison of Shannon-Shannon and lead-lead collision. On these two plots on the left side, we show the the protons to pion ratio, and this shows the radial flow of the particle. This is plotted as a function of multiplicity, and what we can see is that the radial flow is only dependent of multiplicity. Here we show in red the results for Shannon-Shannon, and in blue the results for lead-lead. And you see that the results are really similar. However, when you measure the V2, they are very different. So what we learned from this is that the radial flow depends exclusively on the multiplicity, while the elliptic flow depends also on the initial eccentricities of the collision region. And also on the second plot, we show comparisons of Shannon-Shannon and lead-lead in two different energies. And you can see the full points are the Shannon-Shannon and the open are the lead-lead results, and they all follow the same trend. So we see that the features of the particle production are similar in both collision systems. Okay, then now I'll go to some results in PLED collisions. We have measured the J psi, R PLED, and as I said before, measuring the nuclear modification in PLED collision is important to understand if the suppression that we see in lead-lead collisions is from the hot medium formed, what I mean the QGP, or if it's from cold nuclear matter effects. So we have measured these quantities. On the first plot, we show the results for prompt J psi, and the bottom plot is for non-prompt J psi, which means J psi from B meson. And we have compared with several models that include this particle density function, and they can all describe the results. At least qualitatively, there is a small shadowing at low PT in the case of non-prompt J psi. And we can also use the muon arm to measure the inclusive J-psi at forward and also at backward rapidity. And to measure at backward rapidity, what we do is to use, instead of P-LED collisions, we use LED-P collisions. So the beams are inverted at the LHC. So we have here the results for inclusive J-psi measured at the moon arm and the ones from mid-rapidity, and they are compared to several model calculations, and they are all in good agreement, at least qualitatively. We have also measured the Psi-2S. So here we show the comparison of J-psi and Psi-2S RP-LED. And what we have noticed is that for the Psi-2S, which are these red results, we see a stronger suppression also at backward rapidities. And while for forward rapidity, they are similar to the one from J-psi. And one of the models that can explain this is a model based on co-movers, where the charm can be affected by the interaction with co-moving quarks. And so this is a hint of hot matter effects on Psi-2S formation. We have also measured the elliptic flow in P-LED collisions. And in the case of light flavor, I'm not showing here, but they also show a mass ordering as in lead-lead collisions. So this is a hint of collective behavior in a small system. So we have measured it on the heavy flavor sector. Here we show the results for muons and electrons, muons in blue and electrons in green. And we see a non-zero V2 for both of them. These are electrons and muons from heavy flavor lepton decays. And we have also measured it for J-psi. So on this plot, we show results for J-psi in black and blue. And this is P-LED results, but in red, we show a comparison with the results in lead-lead. And what we see is that there is a V2 different from 0 for high PT, which has a similar amplitude as seen in lead-lead collisions. So this is also a possible final state effect and collective motion from J-psi, even in P-LED collisions. Another measurement that we have performed was the hypertriton. And the motivation of this measurement is to discriminate between nucleosynthesis mechanism in hadronic collisions. And to measure that, we usually do ratios to other particles, since the model calculation, in particular the coalescence model, can calculate this quantity only for particle ratios. So here we show the hypertriton divided by lambda production as a function of multiplicity. In P-LED and lead-lead collisions, P-LED in red and lead-lead in black. And we compare with several model not several model calculations, but coalescence and statistical hadronization model. And what we learned from this measurement is that the best model to describe this hypertriton is the two-body coalescence model, which gets closer to our experimental point. Okay, now I will show some results in PP collisions. The first results that I would like to show is the open heavy flavor production. Here we show the cross-section ratios of charmed lambda over the 0, sigma over the 0, and also we have the key over the 0. And what we have noticed is that these particles ratios were already measured before in electron-positron collisions, but there the ratios were much lower, around 0.1. And now we see these very different results. And this is an indication that there is no hadronization universality between electron-positron and proton-proton collisions. What we would expect from a standard hadronization model is this blue curves that I show here that was produced using PICHA. However, now the PICHA has also a new there are also a new calculation inside which uses color reconnection, and then using color reconnection, Pitya can describe the data at least for lambda and sigma. But however, for this last particle, all models fails to describe. Another result that we have measured is the J-psi cross-section up to very high PT. So we could measure it from 0 to 4 GeV over C. And the high PT points were only achievable thanks to the Alice electromagnetic calorimeter trigger. And also we could perform the separation of prompt and non-prompt J-psi. And from that, we can use the non-prompt J-psi cross-section measurements to calculate the built cross-section, which we show on this plot on the right side. Okay, and another result about J-psi is the J-psi production versus multiplicity. So here we show the self-normalized J-psi as a function of self-normalized multiplicity. And what we see is that there is an increase which is faster than linear. And we have also measured that as a function of momentum for 4 different momentum of the J-psi. And we compare it with Pitya 8, which includes multipartite interaction for the charm production. And we see that Pitya can describe, at least qualitatively, the trend that we see in our data. And we see a higher enhancement for higher momentum. However, the results from forward rapidity obtained using the muon arm shows a linear increase of J-psi with multiplicity, and this is still not understood. Okay, so another result that I would like to show is the measurement of the dead cone effect. So we expect that will be a suppression of the gloom spectrum emitted by a heavy quark within a cone given by this expression, mass over energy. And this could be measured experimentally for the first time by Alice. And what was done was to reconstruct jets containing the G meson, and then the constituents of the jets were reclustered using an algorithm where we could calculate the angular distance from each constituent of the jets. And from that, we could calculate this R factor, which is basically the ratio of the splitting angle distributions for jets containing G meson and inclusive jets. And this was done in 3 different bins of energy. And what we see is that there is a shaded area in each of these 3 plots. And this shaded area is where we expected a suppression of the radiation. And we clearly see this with our data. So this is an effect that we call dead cone effect. Still on the jets, we have measured also what we call groomed jets. And in this case, we can remove from the jet reconstruction the soft wide angle radiations, and then we can reconstruct the core of the jets and the radius of these jets. And what we have seen is that the cores of jets are narrower in lead-lead compared to PP collisions. And this is an important measurement because it's the first direct experimental evidence for this modification in lead-lead collisions. Okay, and another result that I would like to show is the hadron-hadron interactions that we can measure via femtoscopy. And this is a measurement to understand the interaction between hadrons with different quark content. And this is based on the correlation measurement, which is given by this expression, where we have the emission source, the 2-particle wave function, and this experimentally can be calculated like that, where this constant is for the detector effect, and this K star is the relative momentum between the pair of the particles that we are measuring. So on the next slide, I show just correlations as a function of this K star for proton and K minus and proton and omega minus. And what we see here are the results compared to the Coulomb interaction. So these green curves are the Coulomb interaction and a Gaussian distribution for the source shape. And we see that they cannot explain the data. So there is an active interaction that exists and exceeds the Coulomb interaction. And okay, so there are several models that are trying to explain and calculate this active interaction between these particles. And this is the last result that I will show now, which is related to light antinuclei that we can also measure in ALICE. So we have measured these coalescence parameters that we call B2 and B3. On the coalescence model, the production probability of a nucleus is given by this expression, which depends on the mass number A. And we have compared the results from deuterium, and which is the B2, and helions, which is the B3, and we can see that the best wave function that describes it are a Gaussian for the case of deuteriums, and for helions it fails, but it's the only one that we have so far. I don't know, is my time finishing? Probably. Okay, so I only need 2 minutes. I'm sorry, I only need 2 minutes
That's
to say.
That's fine. Yes, yes, please.
Okay, so this was the last result that I wanted to show from PP. Now I just want to say very quickly about the ALICE future perspectives. So this is the timeline, and we are actually here. We just finished the long shutdown too, where several upgrades were done that I will listed on the following slides. In 2025, we will have another long shutdown 3 that will have the installation of IHS3 and also a forward calorimeter. And in 2031, we will have another long shutdown where the ALICE detector will be completely replaced by a new detector. So just to say a little bit what we have on run 3 now, we have this new IHS2, which consists of 7 layers of this CMOS maps, which is silicon technology, which will improve the pointing resolution. Also, the material budget will be much smaller, and the beam pipe will be is smaller inside this IHS, and then we can have a detector closer to the interaction point. We have a new muon forward tracker, which is also based on silicon technology. And we have the TPC with gems, and each allows us to have a continuous readout. So we'll have much more data and much higher luminosity in several collision systems. On the run 4, just to say a few words, we'll have a replacement of the 3 innermost layers of the IHS2 with truly cylindrical silicon layers, which we call wafer scale ultra-thin silicon detectors. And this will also improve our measurements at a very low momentum. And we will have the installation of a focal, which is an electromagnetic calorimeter, and also a hadronic calorimeter. And this will allow us to have measurement at small x. Okay, so this is now my last slide before the conclusion. So in 2032, we expect to have a new ALICE, which we are calling ALICE 3. And this is a detector which is made all using silicon detectors. And this will allow us to have a luminosity a factor of 5 times higher than we have now. And we will be able to go to the ultra soft region of phase space and measure several kind of particles. Okay, then I go now to finally my conclusions. So what we have learned in lead-lead and Shannon-Shannon collisions is that the charm diffusion and energy loss can be constrained by our results of V2 and the nuclear modification factor. We have some thermalization of beauty and also charm. We see that the quarkonium can be regenerated at LHC. And we also have seen that radial flow depends on the multiplicity and not on the collision system. And also the elliptic flow depend on the initial eccentricities of the collisions. In PP and PLED collisions, we have seen several aspects that are similar to what we see in lead-lead collisions, which are indication of a small system created in this kind of collisions. And concerning the future perspectives, we see that we'll have a very high precision data coming soon. So stay tuned for the next presentations about ALICE in the future. And that was all from my side. Thank you very much. And I'm sorry that I took more than expected.
Okay, thank you very much for this very nice talk and with huge amount of results. So we have now time for questions. Please raise your hand. Rogerio.
Thank you, Cristiane, for this very nice talk. As Tere said, it's really a large amount of results. And I'm not from the area, so I want to ask a very naive question. The main focus, I remember, was to find the quark gluon plasma. So what are the best signatures of the quark gluon plasma? And can you say that you have found it?
Yes, all these results that we see for RAA are a clear signature of this quark gluon plasma, like all this suppression of particles that we see when you compare lead-lead to proton-proton collisions. So they are really losing energy on this created medium. This is a clear signature.
Right. You also mentioned thermalization of beauty. Is that also a signature of quark gluon plasma?
Yes, it is also a signature because we expected this asymmetry, this spatial asymmetry, and these are the medium created with very different pressure. And if you have this V2, it's probably that you have a collective motion and thermalization. So we see that very clearly and precisely for light flavor particles because they are very abundant. Oh, sorry, here, because they are very abundant. But we also see for heavy flavor particles. So all of them seems to be thermalized and flowing in this created medium.
Thank you very much, Cristiane.
Thank you.
Any other question? Yes, Edgar, please.
Yeah, thanks so much, Christine, for the very nice talk. I really have an admiration for people doing heavy ions because it seems really difficult, and there are a lot of results that at the end of the day are going to help us all in these fields of high energy especially. So my question is also kind of naive. What are the topics or do you have like any holy grails that are left out to explore that people are very excited about in this field? Let's say, for instance, in high energy collisions in protons, we were searching for the Higgs boson and we found it, and then we're searching for a new particle, but we haven't found it yet. Is there something like that, like a holy grail that is in your list and you really want to see some sort of effect that haven't checked out yet? And the other question may be related. Do you have any tensions with other experiments, like is the case sometimes, like for example, like it was in the, well, not real tension, but there's some discrepancy with some other experiments that imply some left out work?
Okay, so I will start with your second question, okay? You said about tension with other experiment. I have one plot here on my slide 18 that show a difference from ALICE and CMS results. That sometimes this happens, okay? And this is still not understood, but usually we are very consistent. So we have other plots where we show comparisons and we are usually very consistent, but sometimes we can have this unsolved differences. But I think from the upgrades, we'll have more precise data, and then we'll really know what's happening, because we sometimes we have large uncertainties, and then we can still say that within 2 sigma they are still consistent. And about your first question, I'm not sure, because we are, I think the main point that we want to go, it's on this very low PT part to measure this RAA or these particle ratios. And then on the very low PT is where there is some physics that we still want to understand with more precision. And it's also an input for several models that are large, with large uncertainty at very low momentum. So I would go with that direction, that we need to have more precise data at very low momentum. And this is what we are doing with these several upgrades, trying to go down in PT to understand better the things.
Okay, thanks. Yeah, that makes sense. It's consistent with the work that you're doing. Thank you.
Yeah, thank you.
Do we have any other question? If not, then I have a question, a couple of questions, but I will pick up one. One of the main observables is this nuclear modification factor. And you show, for instance, in slide 9, I think it was. Yes, so my question is about the denominator of the factor. So you use your own results on PP collisions for that, how this affect the results is always the same, or you, I mean, what?
Maybe I go to this slide here, right? Where I have the expression. So what we do, we choose, for example, a particle like G meson. And then we measure these particles in lead-lead collisions. And we also measured in proton-proton collisions. But then we need this TAA, which is a normalization, to have the same number of binary collisions in both systems. And then if nothing happens in lead-lead, this should be 1. And what we observe is that something is happening, and this is smaller than 1 because particles are suppressed in lead-lead collisions.
But you use for all the different states the same denominator, I mean, except the TAA, but the PP results are the same. You measure that and you use that.
Yes, but we have to measure for each particle species on the same. Each particle species. Yes.
Okay. And something that also is a little bit different from what we do in our experiments is that your comparisons are more qualitative, in the sense that you have these models, I guess, well, most of them must be phenomenological models. And then in the sense that you don't put limits on the models, but you help the developers of the models. Is that correct, what I'm saying? With your data?
Actually, we provide our data, and the theorists provide the curves. Sometimes they have to use previous results to constrain some of the parameters, but it's not always the case. But for example, some models apply and constrain their parameters to RIC results, and then they try to explain also their LHC. So this happens for some models. This is what they usually do. They use one kind of result as constraint, but then they try to reproduce the next one without any constraint.
So in the sense that you are ahead, in the sense that you provide the data and they can improve their models.
Yes, that's one of the points, that with the data, we can try to constrain the model so they can give back to us what's really happening, because in their models, they can explain what are the interactions, what's happening in this
But it's
medium.
not that you said, okay, this model is completely excluded. You don't say that. You always help this.
Yeah, no, we usually don't say that. We have all of them.
No, I understand. Thank you very much.
Thank you.
Okay. So if I don't see any other hand, so thank you very much again for this very nice talk.
Thank you all for the questions.
Pleasure to hear you. Okay.